This is the final lecture we have for electricity. It's called A Series of Fortunate Events. And the choice or the quote that we have says, "Be miserable or motivate yourself. Whatever has to be done, it's always your choice." And so you can remember that moving forward. So the learning goals that we have for this particular session is that we want to understand the role of a fuse or a circuit breaker. We've already talked about that. We want to be able to calculate the total resistance in series and calculate the total resistance in parallel. And as a result of calculating those resistances, we want to be able to take that resistance and determine the power, voltage, or current at any point in a complex circuit. So, what we already know. We already know that circuits can be wired in series. We already know that circuits can be wired in parallel. We've covered that several times throughout the course of this circuits lesson. We've wired them. We've actually done them in the lab. So we already know that. We learned in the lab that whenever you add resistors in series, it ended up increasing the overall resistance. In fact, you had a relationship that looked like this, where you had the number of resistors down here, and then you had total resistance. We can put it as total resistance at the top, that as you increase the number of resistors, the total resistance increased. And we also saw that whenever you add resistors in parallel, the overall resistance decreased. So if we added the number of resistors in parallel, we see that we drop off the total resistance as we go through there. So that's what we learned in the lab. Now let's take a look at what that actually means. So you have series circuits. A series circuit is one in which the charge only has one choice in which to move. And we use the choice term. It's not a choice, it's which way it's going to be attracted to the most. Whenever you have this right here, neglecting this voltmeter, if you were to look only at the circuit, a charge moving down the wire, never has a choice. It has to go through both R1 and R2. In other words, a charge that travels through R1 has no choice but to go through R2. So because of that, we said that these two resistors are in series. Now the easiest thing to tell with a circuit is that removing one part of the circuit will disconnect the other part. So for example, if I were to remove resistor 2 from the circuit, and by that I mean make it so that you have a break in the circuit. In other words, this is not here, and there's a hole left where resistor 2 was. Okay, if there's nothing there anymore, this circuit would no longer function. Okay, so that's one of the hallmarks of a series circuit. Now, resistors in series are particularly useful whenever you were to take a look at Christmas lights. Christmas lights would be a horrible thing to wire in series because if you have one Christmas light go out, they all go out. Now this right here is from the movie National Lampoon's Christmas Vacation, and you can go ahead and look at it. But you wire millions of lights or tens of thousands of lights, and if one of them isn't out and they're wired in series, you have to test them all. So for example, if I have a whole string of lights and they don't work, it could be this one that doesn't work, but I have no way of knowing until I test them all. Now, fuses and circuit breakers are wired in series, and there's a good reason for that. These are safety devices that if there's a problem with a particular electrical circuit, you want the circuit breaker or the fuse to shut everything off. So what you generally see is you see some sort of voltage source, and then you see a fuse, and then you see all the other resistors that are in the circuit. But what happens is that this fuse or circuit breaker is wired in series with everything else. So that if this thing breaks, everything else is turned off. And it needs to be done that way because if you were to wire it any other way, there would still be electricity that would go to whatever is overloading the circuit to begin with. So these safety devices have to be wired in series. Now, when you calculate the resistance in series, it's nothing more than the sum of the individual resistors. If you have 2 resistors, add the 2 resistors. If you have 15 resistors, add the 15 resistors. This right here is called the equivalent resistance of the circuit. Okay, it's also called the total resistance of the circuit. It's indicated with an R sub S to let you know that it is a series circuit that you are dealing with. But the most common term that you see is equivalent resistance. What it's saying is that if I have, let's say, 1, 2, 3 2 ohm resistors, that those 3 resistors are equivalent to one 6 ohm resistor. So that's what we're saying when we're talking about equivalent resistance. Okay, now the first example that we have says a string of Christmas lights goes out when one bulb is unscrewed. There are 100 bulbs in the string with a total resistance of 150. So what is the resistance of a single light bulb? So we know that we have resistors in series equals R1 plus R2 plus dot dot dot. I'm not going to write out all 100 R's because what we can do is we can assume that since this is a light bulb set that all the light bulbs are identical. When you take R1 and you add it to R2, well, if those two values are the same, that's the same thing as saying R1 plus R1. Or another way of saying that would be 2R1. So when I have 100 light bulbs, what I can do is I can express it as 100 R1. Now that has to equal the equivalent resistance. Now the equivalent resistance in our case is 150. So I can plug in 150. And when you do, you divide both sides by 100. And what you would find is that each individual light bulb gives you 1.5 ohms of resistance. The next one, example A2, says the light bulbs have resistance of 25, 50, and 100 ohms respectively. Determine the equivalent resistance if it is connected to a 1.5 volt AA battery. So the first thing you need to realize is that the voltage has nothing to do with the resistance. Okay, the resistance of the circuit is determined solely by the individual resistor values. These things right here, even though it's a different form of it, you can see are connected in series. I go through this bulb, and I have to go through this bulb, then I have to go through this bulb. So what I can do is I can assign them values. Now it doesn't actually matter which one is 25, which one is 50, and which one is 100. It makes no difference at all, because once you see that they are wired in series, you use the equation resistance in series is equal to R1 plus R2 plus R3. And you see it makes no difference because you're adding them all. You would say equals 25 plus 50 plus 100, or 175. The final example we have here says load 1 and load 2 both have resistances of 5 ohms. Determine the equivalent resistance. So you've got two resistors, they're wired in series, 5 ohms, 5 ohms. You should be able to easily tell me that the resistance in series is going to be 10 ohms. Finding the resistance in series is the first step. We're going to be able to find the current and the voltage and all those other things, but you need to be comfortable with the idea of finding the resistance in series to begin with. Next, we need to talk about finding the current in series. The one rule for current in series is that the current stays the same throughout the circuit. It has to have the same amount of charge. We talked earlier about something called the law of conservation of charge when we talked about electrostatics. Now when we talked about electrostatics, we said if I have a balloon and this one's plus 5 and this one's minus 3, then when they touch together and are separated, they're each going to have a charge of plus 1. And that's what's going to happen because the total amount of charge cannot change. Now remember that current is just the amount of charge that flows through a certain amount of time. So the law of conservation of charge is still going to apply. So if you were to look at it, if I have, let's say, 1 amp of charge right here, there's nowhere else for that charge to go. It's got to go somewhere. So if you were to look at it, I would have the same 1 amp of charge here, the same 1 amp of charge here, and the same 1 amp of charge here. Now I purposely excluded this voltmeter because it's something that we're going to talk about a little bit later. But anytime you have resistors that are in series, they have the same amount of current that goes through each one of them. What's nice about that is if you solve for the current in one particular point, you can apply that current to any other point on the circuit. So this one says, what is the magnitude of the electrical current in the circuit below? So what you can do is you want to use what is known as Ohm's law, and we've talked about it several times. I have a voltage source, okay, and in this case I have to look at the total resistance. So if I want to find the current that is here, I need to look at it in terms of the entire circuit. So I have a voltage that is 9 volts. I have a current, which I am trying to solve for, and I have a resistance that I have to find the equivalent resistance for. Now the equivalent resistance in this case is I have 2 plus 2 plus 2, or I have 6 ohms of resistance. Now I can apply Ohm's law and I can say V equals IR, and I can plug in, I can say 9 equals I times 6, or I equals 1.5 amps. So I can say that the current at any point in this particular circuit is going to be 1.5 amps. It doesn't matter if it's right here at the beginning of the battery. It doesn't matter if it's right here at the end of the battery. It's going to be 1.5 amps no matter where you look. Now we want to take a look at voltage in series. Now the voltage is a little bit different. Remember that voltage implies the push that's moving the charge through the circuit. Now, the key thing for voltage in series, and actually any circuit, is that you have 1.5 volts on the positive terminal of the battery. On the negative terminal of the battery, you have 0 volts. Okay. In other words, the voltage is used as it moves the charge through the circuit. And if you think about it, voltage is most related to energy, and energy is being used in the circuit, usually to heat something up. Okay, so what you need to do is each resistor has what's called a voltage drop. If you think about the voltage as a push, like the electromotive force that's pushing the charge through the circuit, when it comes up against a resistor is something that is pushing back. So when you look at it in those sorts of terms, you realize that if I've got, let's say, 10 newtons of force and it runs into a force or a resistance of 4 newtons, I'm not going to have my same 10 newtons of force after I get through that. Instead, I'm only going to have like 6 newtons. Now that's an imperfect analogy, but it's a way of being able to visualize it. So now let's take a look at the voltage drop. This right here is just Ohm's law. It's Ohm's law. Now, if you were to take a look at this, though, really what you're doing is you're taking the current, which is the same everywhere in a series circuit. Everywhere in the circuit has the same current. And if you want to figure out how much the voltage drops from here to here, all you need to do is take the current and multiply it by the individual resistor value. Now, this might make a little bit more sense once you've seen an example of it. So let's go ahead and take a look at an example. Oh, we've got to cover resistors in series first. So resistors in series are useful in the sense that you can use them in joysticks, because whenever it does that, the current will change. Whenever you add a resistor, it changes the current. Whenever a computer can detect that lower current value, what it does is says, okay, this has been activated. So generally you see that with joysticks. Whenever you see like an Xbox controller or a computer, this is a really old joystick that you're seeing there, but whenever you see that, the computer is detecting, hey, there is a constant motion in that direction. It's different than a button. A button works using a capacitor, and whenever you use a button, what you do is you push it and it discharges, and no matter what you do, it can only go so fast. If you push that button as fast as you can, it's not going to register as quickly as you can hit it on the computer, because the capacitor needs to recharge and recharge. Okay, the joystick doesn't work that way. You need that continual flow of movement, so that's why those use resistors. So example C1, it says, using the picture below, determine the value of one resistor. So if you were to look right here, it's kind of hard to see, but you can actually take a look and you can zoom in a little bit and you can see what the current reading is. Now if you were to look right here, the current reading, it comes out to about 2.2 on the scale. Now if you were to look at this clip right here, the clip right there, and that's really hard to tell, says that it's actually on the 500 milliamp scale. So what this is this is not 2.2 amps, because when it's on the 500 milliamp scale, what it's saying is when it's right here, that's 500 milliamps. Well, 500 milliamps would be 0.5 amps. So there's no way that you can get a reading of 2.2 amps whenever it doesn't go to the full value. So what you need to realize is that by being in this middle chord right here, what it does is it moves the decimal over 1. So the reading on this particular one is 0.22 amps. Now that you know that it's 0.22 amps, you can read the voltmeter. The voltmeter is set at exactly 2.2 volts. Okay, so now that we have the fact that we have a current and we have a voltage, we can use those values to solve for the resistance. Now when we solve for the resistance in this case, what we're solving for is the total resistance of the circuit. So we're treating these two resistors in series as if they're one thing. I would use Ohm's law. I would say V equals IR, and I would say that I have 2.2 volts, equals 0.22 amps times the total resistance. So the total resistance ends up being 10 ohms. Now, if these two resistors were any different, I wouldn't be able to say, hey, this one is 3 and this one is 7, this one is 1 and this one is 9. But since these two resistors right here are equivalent, what I can then say is I can say that I have the resistance in series is equal to 2R1. Or in other words, 10 equals 2R1, or R1 equals 5 ohms. Now this one says determine the power dissipated by the 10 ohm resistor. Okay, so when I look at this 10 ohm resistor, I have a couple of choices. Okay, for this one particular 10 ohm resistor, I'm trying to solve for the power. Now we have several equations that deal with power, and you can do these any which way you want. The first equation is P equals I squared R. The second equation is P equals V squared over R. And then you can also use the equation P equals IV, depending on what you want to do. Now I'm going to use this equation right here because it is the most complex one for you to deal with. Okay, this is really easy to deal with because you can just solve for the current and you've got the resistance value and it's pretty easy to do. This one, there are certain circumstances where you have to use this equation. So we're going to go ahead and use that one and for this particular example, even though there is an easier option. So the first thing that I want to do is I want to say, okay, I have a voltage of 9 volts. I have a total resistance, because these are wired in series, of 30 ohms. What that allows me to do is that actually allows me to solve for the current, and I can say Ohm's law, V equals IR, and I can say 9 equals 30 I, or the current is equal to, well, it ends up being about 0.3 amps. So now, that is 0.3 amps at all places in the circuit. So like I said, I could take this 0.3 and I could multiply it, or I could square that value and multiply it by 10, and I would get a value of 0.9 watts, and that's good. But I wanted to look at the idea of the voltage drop. Okay, I want to know what the voltage drop is for this particular circuit. Now remember, the voltage drop represents the current times the individual resistor. So what I want to do is I want to find the voltage drop for the 10 ohm resistor. And when I do that, it ends up being a voltage drop of about 3 volts because the current times the individual resistor. So now if I were to use this voltage drop value, I could then say, okay, well now I can plug it into this equation right here. And I have a voltage drop of 3. That 3 term is squared. 3 squared is 9. And then you divide it by the resistance value. Well, the resistance value, the resistance value in our case was 10. 9 divided by 10 is 0.9, which is the same thing that I got over here. Any of these three equations will work whenever you're trying to find the power dissipated. It's best that you've used the one for the particular situation that works for you. In this one it says 3 light bulbs have a resistance of 25, 50, and 100 ohms respectively. Determine the voltage at all points on the circuit if connected by a 1.5 volt battery. Well, the first two are easy. You've got 1.5 volts and you've got 0 volts. So any point after this last light bulb, it's 0 volts. And any point up until the first light bulb is 1.5 volts. So really what I need to do is I need to find the voltage here, and I need to find the voltage here. Okay, in order to do that, what I need to do is I need to solve for the current that's overall. So I have the voltage is 1.5 volts, and I have the total resistance is 25 plus 50 plus 100, and I can say that's 175 ohms. Now once you do that, you can solve for the current. You would say V equals IR, and you would plug in 1.5 and you plug in 175 I, and you would solve for the current to be, if you round it, it's going to be about 0.0086. Now remember, in order to solve for the voltage drop, you have to multiply the current times the individual resistor value. Now the individual resistor value for the first one is 25. So I would take 0.086 and I would multiply it by 25, and that would now give me the voltage drop. And the voltage drop, when I multiply those two things out, is about 0.215. And then I do it for the second bulb, which would be 0.0086 again, but this time multiplied by 50. And when I do that, I get a value of about 0.430, which you would expect. And then for the last one, you would do 0.0086 times 100, and you would get a value of about 0.86. Now, these are the individual voltage drops. So what I'm saying is, after the first light bulb, I need to take away 0.215 volts. Well, how many volts did I have to begin with? Well, I had 1.5 volts. So when I take 1.5 volts and I subtract that, now at this point where I'm in between the first two light bulbs, my voltage is now 1.285 volts. Now, I now have the second and third light bulbs. In between the second and third light bulbs, I have a drop of 0.430. And when you subtract those values, you get the voltage going into the third light bulb, and that would be about 0.855 volts. And then you could check the last value. You would say, okay, well, I have 0.855 volts, and I have 0.86, and I subtract the two. I end up with a voltage of negative 0.05 volts, but I'm supposed to be at 0, and that throws some people off. And people say, well, I don't know what I did wrong. I don't know what I did wrong. You didn't do anything wrong. What you did is you rounded this number. Whenever you rounded that number, you introduced a source of error. But it's just a very, very, very small error. This right here is negligible. You would say that it's 0. Okay, so series circuits in action. Like we said, series connections are useful because if one connection they all go out, if one goes out, they all do. They're useful in fuses and circuit breakers, and they're nice in being able to manipulate the voltage of a circuit for things like, a remote control or trying to use directions on a gamepad or something like that. Now we need to talk about parallel circuits. Now parallel circuits are different from series circuits in that there's a choice. We use the term choice in quotation marks because the electron doesn't choose, but has a choice of which path to move down. Now, the other thing about a parallel circuit is that when you remove one path, it does not stop the others from functioning. So in other words, if I'm a charge moving down a wire, and I come down here and I get to the fact that I get to this what's called a junction right there. At that particular junction, the charge can go down R1, R2, or R3, and those are all ORs. It's not an AND. So because of that, these three resistors are said to be wired in parallel, which means that the charge can choose which direction to go. What it will do is it will always choose the path of least resistance. So for example, let's say that I have a buildup of charge here for whatever reason. There's a buildup of charge there. And there's a buildup of charge right here. Well, then this charge will take the path of least resistance and go this way. So because of that, this charge is predictable as far as how much charge is in each resistor, and we're going to talk about that. But the other hallmark of the parallel circuit is the fact that if you were to remove one of the branches, let's say I take R3 and I unscrew a light bulb, or somehow I break this wire, it does not stop the other two from functioning because the charge can still go through those into the other side of the battery. So that's the two primary things that distinguish a parallel circuit from a series circuit. Now, resistors in parallel. If the circuit breaks in one location, there are always alternative pathways, and that's the key. And what you see here is you see a light bulb that has been unscrewed. If you take that light bulb and you unscrew it, there is still the ability for it to go through these other two to the other side. So that's the key, is the fact that it's an alternative pathway is what makes a resistor in series. Okay. Next, whenever you are calculating the resistance in parallel, this got thrown off as it was exported, you get the formula 1 over Rp equals 1 over R1 plus 1 over R2 plus dot 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 dot. So these arrows right here are just trying to show you that those are subscripts. So what you get right here is you get the idea of the resistance in parallel is equal to 1 over. So it's not just adding them anymore, it's adding their inverses. And that may seem like a small distinction at first, but it really is a big deal. Whenever you added resistors in series, what you ended up with is you ended up with a larger resistance overall. But just to kind of show you what you've got going on here, if you were to take resistors, let's say, let's start off easy. Let's say if we have two 4 ohm resistors. Well, if those resistors are wired in series, you would have a total resistance of 8 ohms, where the total resistance is greater than any one resistor. If you were to do the same thing with parallel circuits, you would say that 1 over 4 plus 1 over 4 is equal to 1 over Rp. Well, 1 over 4 plus 1 over 4, please get this right, is not 2 over 8, but instead it is 2 over 4. So you get this value, you would say that this is 2 over 4. So now you're saying that 1 over Rp is equal to 2 over 4. At this point you can cross multiply, or if instead of cross multiplying, the easiest thing to do is what you do is called flipping it, or taking the inverse. When you flip it or take the inverse, what you're doing is you would say that you'd have Rp over 1, which is the same thing as Rp, equals 4 over 2, or 2. That's the same thing that you would get as if you cross multiplied, but for some reason it's a little bit quicker. So if you look, the total resistance in parallel is less than the individual resistors. Okay, so when you add resistance in parallel, what you're doing is you're decreasing the overall resistance. And let's go back to the picture to kind of look at why. If you were to look at it, if I have a single resistor with a value of 10, there's nothing you can do about it. You have a resistance of 10. But by adding a second resistor of 10 and producing the ability for it to choose, okay, if it can go this way or this way, you're introducing a new option that would reduce the overall resistance or the overall load on each circuit, because a charge can go this way or this way. And in doing so, it decreases that push back because there's another pathway. So let's look at it in terms of an example. Once again, we have our string of light bulbs. There's 10 light bulbs in the string this time. Okay, we decided to reduce it down to 10 for reasons that we'll show you in just a second. But there's a total resistance of 1.5 ohms. So we would say the resistance in parallel is 1.5 ohms. And we know that there are 10 bulbs, but instead of writing out R1 plus R2 plus, we're not going to do that because that would take a long time. So instead what we'll do is we'll say, if I had 2 light bulbs and they were 1 over R1 plus 1 over R2, you could add these together. Now you wouldn't add them together and you wouldn't say 1 over 2R. Okay, instead you would say that it would be 2 over R1. Okay, because you're adding these two fractions together. So now what it looks like when I'm talking about resistors in parallels, you'd say 1 over Rp is equal to, I have 10 bulbs. If I have 10 bulbs, it would be 10 over R1. Now we can replace our resistance in parallel value with the value they actually gave us, which was 1.5. At this point, you could cross multiply, you could flip it, you could do whatever is necessary for you to solve this thing. The easiest thing in this particular case would be to cross multiply. Okay, when you cross multiply, you get R1 times 1, which is just R1, is equal to 1.5 times 10, which is 15 ohms. Now, if we look at another example, it says the resistors have values of 5, 10, 20 respectively. Determine the equivalent resistance. Now, it tells you the voltage of the battery. Once again, the voltage of the battery is irrelevant in determining the overall resistance of the circuit. So now I have resistors. I've got to say when they come through here, I have a choice of going through R1, R2, or R3. So because of that, these resistors are wired in parallel. So I will use the parallel formula. 1 over Rp is equal to 1 over 5 plus 1 over 10 plus 1 over 20. Now at this point, Adding resistors in parallel can be somewhat cumbersome, and I know you can look at this and you can find a common denominator relatively easily, and you can add them up and you can make it work. But it is much, much easier in your calculator if you were to do this. If you were to enter the number 5x to the minus 1. Okay, the x to the minus 1 term means that. So whenever you take 1 over 5, that's the same thing as 5 to the minus 1. So if you were to do this, plus this, plus this, and hit enter, what that would give you is that would give you the value of all of those fractions added together. Okay, whenever you do that, okay, you would get a number, 1 over RP is equal to some number, is what your calculator would tell you. Now remember, I don't want to know what RP is, or what 1 over RP is, I want to know what RP is. So what I would want to do is I want to do x to the minus 1 of my answer and do it to both sides. Now, what happens when you do 1 over RP to the negative 1? Well, if you did 1 over x, that would be the same thing as x. So if you did this, you get RP. And since we did it to one side, we did it to the other, you get whatever number the calculator gives you right there, x to the minus 1, and you should be able to get a value of 2.73 ohms. Now check yourself in your calculator that you have that you're going to use on a quiz or a test, because you need to be able to do this on your own. Now, the last example, we're going to do it without the trick that we just showed you, because it's relatively simple. So you have two 5 ohm resistors that are wired in parallel. So I want to find the equivalent resistance. I would say 1 over RP is equal to 2 over 5. Now the reason why I know it's 2 over 5 is they're identical resistors. 1 over 5 plus 1 over 5 is equal to 2 over 5. At this point, I can flip them, or I can cross multiply, whatever I'm comfortable with, and you get RP over 1, which is just RP, is equal to 5 over 2, or 2.5 ohms. So anytime you have two resistors that are wired in parallel, and they have the exact same resistance value, what you can see is you can see that the resistance value is going to cut in half. Now we need to talk about voltage and current in parallel. Now, we talked about current first because current stayed the same whenever we were talking about series circuits. Now we're talking about voltage first, and the reason for that is that when you have wires that are in parallel, the voltage is going to be the same. Okay, wires in parallel will have the same voltage. That's why whenever you use one of these strips where you're plugging one outlet into the wall and then you've got 5 or 6 different outlets coming out of it, that they can all be used to power the same devices. Now all of your devices are designed for 110 volts to 120 volts. Now they're designed for 120 volts, but this is kind of the minimum value that you get from an outlet. So all of these things have to have 120 volts, and if they didn't, it wouldn't work. So because of that, whenever you wire something in parallel, it has to have the same voltage. Now if you think about voltage, voltage is the energy per charge. So if this one charge has 120 joules, it's the energy per charge, it doesn't matter where that charge goes, it's still going to have 120 joules per charge. Now that's a simplistic example, but it's showing you the idea that because of what voltage is, it is not going to change depending on which branch it takes. So in our particular case here, we'd have 9 volts in this branch, we'd have 9 volts in this branch, and you'd have 9 volts in this branch. Now that's the other thing that people think, is they think, okay, well wait a second, if it's 9 volts, shouldn't those 9 volts be split up into 3 separate branches? And the answer is no, because once again, it's the energy per charge. If one charge goes down here, it's going to have the same energy for that one charge. It may have less charges, which we'll talk about with current, but at the same time it's going to have the same energy for each charge. Okay, so we want to look at this. It says, example E1, determine the voltage in the 10 ohm branch. So now remember, if I'm trying to find the voltage in the 10 ohm branch, what is the same in every branch? And you can say, well, it's the voltage. So this one's really easy in the sense that I have a 9 volt battery, And remember, that's the energy for each charge. So this right here is going to be 9 volts, and this right here is going to be 9 volts. And it makes it really easy to do these. Like I said, you've just got to be straight with what's the same. Current's the same in series, voltage is the same in parallel. So now let's talk about current. Now current uses something called the junction rule, which is really just another way of saying the conservation of charge. Basically what it says is that if you have, let's say, I'll just make up a number for this circumstance. Let's say I have 1 amp of charge right here. It's going to be pretty close to that, but it's not exactly. But if I have 1 amp of charge right there, I have to have 1 amp of charge right there, because conservation of charge. You can't create charge, you can't destroy charge. You can kind of play around with it a little bit, but because of that, you've got to have the same amount of charge both here and here. Now, the problem is that the charge is split between 2 branches. Okay, I have no idea at this point how much charge is in which branch. Now, you could probably figure it out based on the fact that these 2 resistor values are the same. You've got 5 ohms and you've got 5 ohms, which means that they're each going to take half the charge. Okay? But if we were to take a look at it from a different perspective, what if we changed this value? What if we made this one 1 ohm and this one 10 ohms? Well, what you would expect is you would expect more charge to go through the 1 ohm resistor. And the reason for that is it will take the path of least resistance. Now, that doesn't mean that all of the charge will go in this branch. There will still be some charge that goes through the 10 ohm branch, but not nearly as much. Now, we can actually figure out what the current is in each branch by taking the voltage drop, okay, which is the same in each branch. Okay, in our case it'd be 9 volts, and multiplying and then using the resistance of an individual branch. So using these 2 values right here, I can solve for the current in an individual branch. So now, as an example, we want to determine the total power dissipated by the circuit and by each resistor. Now, in order to find out what the power is going to be, I can actually figure it out multiple ways. I can say P equals V squared over R. I can say P equals I squared R. And I can use P equals IV. Now, I can do that for each one. Now, if you were to take a look at this, the easiest thing to do is to look at the circuit in pieces at this point. So, if this one dissipates a certain power, then this one is going to dissipate a certain power. Now, the easiest thing to work with in our case is going to be voltage, but the problem is the voltage is not given to me by the battery. But if I were to look at the individual branch, I can say V equals IR. Or in other words, I could say 2 times 8 is equal to the voltage, or I have 16 volts. Remember, that means that I have 16 volts right there. But remember, voltage is the same in each branch. So I can also say that I have 16 volts right there. Okay. You have a myriad of options as far as how you want to solve this now. And any way will be correct as long as you imply the correct method. But just to show you that we can do it this way, I'm going to go ahead and solve for the power in the first branch just by doing I squared R. So I would say 2 squared times 8. That's this formula right here. Whenever you do that, you get 4 times 8, and you would get 32 watts. So you would say that there are 32 watts that are used in this particular branch. Now, if you want to take a look at the next one, you can say, all right, well, in the next branch, I've got voltage and I've got resistance. So I want to use the idea that I've got 16 squared divided by 24. Okay, now when you do 16 squared and you divide it by 24, that's a little bit more complicated. You might actually have to go to a calculator for that. So you would do 16 squared divided by 24, and you would get a value of about 10.7 watts. Okay, so I have 32 watts by this one, and I've got 10.7 watts by that one. So the total of the circuit would be those two added together, which would be roughly 42.7 watts. So now we look at the next one. It says, determine the voltage of the battery in the circuit below. If you were trying to figure out the voltage in this particular battery, you do what we just did. You solve for the voltage in one branch, realize that it's the same in this branch, and that it's the same in the battery. So you would say 2 times 8, that's 16 volts, which makes that 16 volts, and that's as easy as it is. The next one asks us to find the total current throughout the circuit. Okay, in order to find the total current, I need to know what the current is in this branch, and I need to know what the current is in this branch, so that I can add those two currents together, and I can get the total current. Okay, so I can use Ohm's law. I can say V equals IR, and I can say I've got 12 volts equals I and 5. Take both sides divided by 5, and when you divide both sides by 5, you get a current in this particular branch of 2.4 amps. But remember, that's only part of it. That's our I1 value. Now we got to look at it in terms of our I2 value. So the problem is I don't have the voltage here. But remember, the voltage is the same in each branch. So I could say that the voltage is 12 volts in this branch as well. So I would do V equals IR, and I would say 12 is equal to I times 10. Divide both sides by 10, and when I do that, I would get an I is 1.2 amps. So this right here is 1.2 amps. Now I need to take those two values and add them together to get a total current of 3.6 amps. The last one that we have says determine the current in the 10 ohm branch. So I want to know what the current is here. Well, there's not a whole lot to go on except for the fact that I know I've got the battery, which means that this right here is 9 volts in that branch. I can then use Ohm's law, V equals IR. 9 equals I times 10. Divide both sides by 10, and the current is 0.9 amps. Now, that's it for this particular lecture. Now, I would encourage you to take a look at how you can combine series and parallel resistors together. In other words, what would happen if I had something like this? Is it a series circuit? Is it a parallel circuit? Well, it depends on how you look at it. The easiest thing to do would be to combine these two things because those are clearly parallel. And remember, whenever you have two resistors in parallel, you can treat them as one equivalent resistance. Or you could say that. And you would use the formula to plug that value in. Well, now when you look at it, it sure looks to me like these are 3 resistors wired in series. So think about that before you come to class, and let's see what you think of that as you go.